A defense that looks strong on paper can collapse in seconds if you rely on static passwords. But the modern internet secures everything we value using a completely different trick, one built entirely on multiplication. In the physical world, a signature is a unique mark of ink. But in a digital system, everything is just numbers, meaning any mark can be perfectly duplicated. So how do we stop infinite forgery? To fix this, we split identity squarely in half. We generate a matched pair of digital keys. One is locked away as a secret, while the other is broadcast to the world. But why do this? These keys are not just random text files. They are deeply connected through the properties of enormous prime numbers. Multiplying two giant primes creates a foundation that is easy to build on, but hides a secret. This creates what mathematicians call a trapdoor function. Dropping through the trapdoor is fast and effortless for anyone, but trying to climb back out without knowing the secret lever requires an impossible amount of computational power. That secret lever is your private key, derived directly from those original prime building blocks. Because only you know the starting blocks, only you hold the exact mathematical value needed to safely unlock the reverse path. Before we use this lock, we hit a speed limit. Documents are massive, and running millions of words through complex prime multiplication is too slow. So we must crush the data into something smaller first. We pass the file through a one-way algorithm that spits out a short fingerprint. If even a single comma changes in the file, the resulting fingerprint changes completely. But a fingerprint alone is not proof. We need a way to tie that fingerprint to you. We take the tiny digest and apply our deeply guarded secret key. We subject the fingerprint to an intense mathematical transformation that only our numbers survive. The final result of this transformation is a brand new giant block of numbers. This is your digital signature. It is completely unique to both your secret identity and the exact contents of that file. You bundle the original document and this new signature block together, sending them across the wild internet. Anyone watching the network wires can see both pieces, but can they alter the contents without destroying the math? Suppose a hacker intercepts the package in transit. They desperately want to change the payment amount. They rewrite the text, but the moment they do, the original fingerprint no longer matches the newly altered document. To make the fake document look legitimate, the hacker must somehow generate a new signature. But the required mathematical transformation demands the secret key, which they do not have. Without it, the equations simply collapse. Meanwhile, the real recipient gets your package. They want to know if it is truly from you. They take your publicly available key, which you broadcasted earlier, and they push it into the giant signature block. This is where the magic of the trapdoor happens. The public key perfectly reverses the intense transformation you applied. The giant block of numbers unwraps itself computationally, revealing the original fingerprint tucked safely inside. The recipient then takes the document they received and runs it through that exact same crushing algorithm. They generate their own fingerprint and hold it up next to the unwrapped signature fingerprint. What happens next? If those two fingerprints match perfectly, character for character, the proof is mathematically absolute. The document was not altered in transit, and it could only have been sealed by the person holding the secret key. The only way to forge this seal without the secret key is to derive it from the public one. To do that, an attacker must take the enormous mathematical modulus and split it into its primes. For numbers large enough, this prime splitting process takes infinitely more time than the universe has been alive. Even with giant server farms running for thousands of years, the mathematical wall stands firm against brute force. Every time your device connects to a bank or downloads a critical update, it relies on this exact process. Trust on the modern internet isn't based on physical walls, but on the unyielding certainty of primes.